Hey everyone, this video is about number-based questions and mental arithmetic in section 1 of UMAT. So this video is number 5 in the series. You can see it's the final video in the problem-solving subsection. Before we get started, just a few basic tips. I've broken this video into 3 subsections: probability, number-based questions, and mental arithmetic. So with probability, we'll go through the concepts of consecutive probabilities and either-or probabilities, and also the idea of replacement. So you might have come across these ideas in high school maths, but I'll go through them quickly just to refresh. With number-based questions, I'll just do a few based on a recent style I've seen pop up a few times in recent years. So that is questions where you're asked to work out the number of times you have to do something in order to be sure of a particular outcome. And to do that, I approach it using a worst possible event technique that I'll go through with you. And just finally, we'll do some mental arithmetic. So these won't be questions so much as just illustrations of how to use mental arithmetic. Because obviously in the real UMAT, you don't have a calculator, and occasionally you are asked to do some pretty tough calculations. So we'll go through ideas of rounding, as well as being comfortable with shifting decimal points to work out what 1% and 10% of different numbers are, and using them as building blocks to work out more precise estimates of numbers and of percentages. And just that final point there is saying we'll also deal with ideas of using real numbers in questions where we're just given fractions. So this is kind of the scope of the video, and we'll go through each subsection one by one. So let's begin with some probability-based questions. Question 1. There is a bag containing 3 red marbles, 2 green and 4 yellow. What is the probability of first selecting a red marble and then selecting a green marble if they haven't been replaced? So this question demonstrates the idea of consecutive probabilities, which is when you have 2 or more events and you're being asked to calculate the probability of all of those events occurring. So in other words, the first event here is first selecting a red marble. That's the first thing we have to satisfy. So what are the odds of initially picking a red marble out of the bag? Well, we've got 3 red marbles here, so I'll write down 3, and that's out of a total of 9. So 3 over 9. That's the probability of first selecting a red marble. But we're being asked what's the probability of doing that and then also selecting a green marble. So ask yourself, what's the probability of then selecting a green marble if those marbles haven't, or if that one marble from before hasn't been replaced? So in other words, we've taken one red marble out of the bag, so we've only got 8 marbles remaining, and we've still got 2 of those which are green, so it'll be 2 on 8. So these are the 2 probabilities of first selecting a red marble and then selecting a green marble. Now if we're being asked what's the probability of both of those occurring, all we have to do is multiply the 2 together. So that comes to 6 on 72. If you simplify just by dividing both by 6, you can then get that down to 1 on 12. And so that would be the answer. The answer would be B. So this just illustrates the idea of consecutive probabilities. In any question where you're asked to work out the probability of several things occurring, this is the approach. Just multiply the individual probabilities together to get to the answer. So as I mentioned before, it'll be 1 on 12. Question 2, it's the same scenario, but we're now being asked what is the probability of first selecting either a red or a green marble and then selecting a yellow marble. So it's similar to before in that we've got 2 separate events, but the first event here, where we have to select either a red or a green, touches on a different concept to what we've gone through before. So when you're asked to what's the probability of picking either a red or a green, we have to add together the probabilities of picking a red and picking a green. So in other words, initially the chance of picking a red would be 3 on 9. The odds of picking a green would be 2 on 9. And so to pick either one of these 2, all we have to do is add them together. So that would give you 5 on 9. That's the principle of either or probabilities. When you've got 2 events or 2 outcomes, and all you need to do is achieve one of the 2. In that case, all you do is add together the 2 individual probabilities to find the overall probability. So we have a 5 on 9 chance of first selecting either a red or a green, which makes sense really when you think about it, because there are 5 marbles which are red or green out of the 9. And now the second part of the question is saying that we then select a yellow marble, assuming the marble from before has been put back in the bag. So this is the first event here, 5 on 9, as we went through before. Now the second event will be picking the yellow out of the bag. So there are 4 yellow, and given the marble is being replaced, that's out of, again, a total of 9. So 5 on 9 and then 4 on 9. And we're being asked, what's the probability of both of these occurring? So again, it's the same as the previous question. It's a consecutive probabilities question. So all we have to do to work out the total probability is multiply these two. And that would come to 20 over 81. Now, have a quick look to see if you can simplify that, but I don't think you can. And as you can see from the answers, that is option C. So we can go straight for option C in this case. Going to question 3, it's the same setup, but the new question is, what is the probability of selecting either a green marble first or a yellow marble second, assuming the marbles are replaced? So it's a similar principle to before, where we're adding together two individual probabilities, given it's an either-or type of question. So if we're looking for the odds of selecting a green marble first, that would be 2, because there are 2 green marbles out of a total of 9. Now it's saying that the marbles are replaced, so that green marble will get put back in the bag. And the second probability is picking a yellow marble second. So there are 4 yellow marbles, and again it's out of 9 because we've got that one marble replaced again. So those are the two individual probabilities. And we're looking for the probability of either one of these two occurring. So if you're looking to work out either one of these two, we just add them together. So that would give you a total of 6 on 9, which simplifies down to 2 on 3, which is option A. So that's it for the probability part of the video. It's all pretty straightforward, and I think those two concepts, consecutive probabilities and either-or probabilities, are really the cornerstone of any probability in UMAT. Like I mentioned before, in the real paper, the questions themselves would probably be dressed up in a bit more of a narrative and a bit more complexity, but the probability itself that would be required of you would probably come back to these two concepts. So that should be enough for the UMAT exam, I'd say. We'll do some number-based questions now. So have a look at this one for a minute. There are 13 cards on a table, 3 red, 4 blue and 6 white. If you pick up 2 cards at a time, what is the minimum number of times you would need to do this to ensure you had at least 2 of each color card? So in other words, what's the minimum number of pairs you'd have to pick up to ensure you had 2 of each color card? Just notice the wording of this question. It's the minimum number of times you have to do something to be sure of an outcome. It's not the minimum number of times you have to do something to have a chance of an outcome. So it's to be sure of an outcome. This style of question I've seen a few times in recent years, which is why I've put it in here. It's basically just asking you, what is the worst case scenario that could occur, and how many times would you have to do something in that event to achieve a certain outcome? So really it's just a case of imagining the worst case scenario. In this particular question, the goal is to pick up 2 of each color card. So ideally, when we're picking up our pairs, we want a pretty even spread of red, blue and white, because we want to get to the point where we have 2 of each color as quickly as possible. That's the best case. So if that's the best case, what's the worst case scenario? Well, I would say it'd be if you pick up a lot of the same color card again and again, because then you just have a lot of one, but you wouldn't have 2 of each color. So that's the process we have to go through here in working it out. I'm just going to sketch up the different cards because I think it always helps in UMAT to visualize what we're dealing with wherever possible. So 3 red, 4 blue, and 6 white. So as I mentioned before, the worst case scenario would be that you pick up a lot of the same color card, such that you don't get a nice even spread and end up with 2 of each color. So if we imagine that, let's imagine our first pair are both white. I'm just going to start with white because there are a lot of them. Second pair also white, and third pair white. So our first 3 pairs are all white. Then we can go to the blue column and we'll pick up a blue pair there and a second blue pair. So again, at this point we've picked up 5 pairs and all we have are the 6 white cards and the 4 blue, but no red. So we still haven't satisfied our condition of 2 of each color. You can see at this point, whatever we do next, there's only 3 reds left. So the next pair we pick up will both be red. And at that point, you can see we'll have 2 of each color. But this is the worst case scenario. This is the longest it could possibly take to get 2 of each color. and you can see it's a total of 6, which is why the answer here would be 6. That's the basic approach to these. It's just a case of imagining the worst case scenario and seeing what that is. And it's fine to write it out and just sketch it up like this. It still doesn't take too long to work out. I'll just do one more very similar question to illustrate this approach again. So it's the same setup, but the new question is, what is the minimum number of pairs you'd have to pick up before you could say with certainty that you picked up at least 4 cards of the same color? So it's kind of the opposite of before. Whereas before the goal was to get as many, the goal was to pick up an even spread of a few different colors. In this question, the goal is to pick up 4 cards of any one color. So we want to pick up just a lot of one single color, even if it's at the expense of the other 2 colors. So that's the best case scenario. Therefore, the worst case scenario would actually be to pick up a pretty even spread of cards, because that way you take a long time to get 4 of any one color. So again, I'll just begin by sketching up all the different cards. And I'll show you from there an approach for how to pick cards as evenly as possible. In other words, 4Bs. In other words, how to select them in such a way that you take the longest time possible to get 4 of any one color. So the way I do this is just go along each row. So let's say we begin by picking up a red and a blue. That's our first pair. The next pair will be a white, and then when you reach the end of the row, go down to the next row. So we'll pick another red. So the first pair was the red and the blue. The next pair was the white and the red. Then the next pair will be the blue and the white. Keep going. So keep going to the row down. So another red and blue here. You can see that really there's no chance of getting 4 reds. To get 4 blues, you'd have to have all 4, and likewise with the white, you'd have to get down to this W here to have 4 of them. So at this point, we're still fine when we've picked up 1, 2, 3, 4 pairs. Now the next pair is tricky because we'll pick a white. That's fine. That's just the 3rd white we've picked. But you can see whenever we pair this white with, we're going to get a 4th of a particular color. So if we pair this white with a blue, then we'll have 4 blues picked up. If we pair it with another white, then we'll have 4 whites. So it doesn't really matter which way we go. At this point, this is the pair where you will definitely have 4 cards of at least one color. And so given we've picked up 4 already, this one here will be the 5th. And for that reason, when you pick up 5 pairs, we can say with certainty that you'll have at least 4 cards of one color. But this technique of going across the rows in this way, it's the easiest way to, first of all, ensure that you are picking up an even spread of cards, but it also helps you to visualize how many of each you've picked up. You can quite easily go down the columns and see how many you've done at any given time. So in this case, you can see the answer would be 5. So these last 2 questions show kind of the same type of question and the same approach. It's just that one question asked us to find an even spread of cards, whereas the other question, this question, asked us to just find a lot of one particular card. And you can see the 2 different approaches to solving. So that should do us for this particular style of question. We'll move on to the next one. This question is a bit different in style. I won't read through all the instructions, but pause the video and take a minute to do it yourself. It's really just a case of reading carefully, setting out nicely, and then doing a bit of multiplication. So there's nothing too difficult despite how much information there seems to be. So in this game you can see there are 2 players. Initially one card is taken from the deck, and after that player A and B alternate back and forth, beginning with player A, and they multiply. Each player multiplies their initial score by their 1st and 3rd card, and divide it by their 2nd and 4th. So all we need to do here is be very careful with working out who picked up what card and in what order. And now the order is given here, and you can see that there are 9 numbers in total. And it says that each player only picks up 4 cards after the initial card is drawn. So we can assume that this 3 here is the initial card that's drawn. So I'm going to sketch up A for player A and B for player B. We can see that for both players, they initially pick up a 3. Now it says thereafter player A picks up the 1st card. So player A will pick up the 6 there. And then they'll also pick up every 2nd card from there because they alternate between player A and player B. So 6 and then 2, and then the 8, and then finally the 4. So every second card from that 6. Player B will just do the same thing, but they'll begin with the 5, and then skip over to the 3, then the 1, then the 5. Now the rule with scoring is given in these 2 dot points here. It says that they, from their initial number, which is 3 for both of them, based on the first card drawn here, they multiply that score by the first and third card. So we'll put just a times sign in here, because we're timesing that by the first card, which is the 6, and also by the third card they pick up, which is the 8. Likewise, same thing for player B. And they divide their score by the second and the fourth card that they pick up, which will be in here. So I'll put that there. So it's a very ugly way of sketching out an equation. But that's basically what the scores will come to in the end. You can re-sketch it up if you want. Might just do it down here, player A. Therefore, we'll have 3 times 6 times 8 on top. So 3 times 6 times 8 over 2 and 4. So 2 and 4. And then B, they're very similar. So we'll just write for them 3 times 5 times 1. 3 times 5 times 1. 1 doesn't really matter. Doesn't make a difference. Over 3 and 5. So 3 and 5. When you do it this way, you can quite quickly see for B that just equals 1 because it's 15 over 15. So that's just a score of 1 in the end. Now for A, just a bit of quick maths, 3 times 6 times 8 over 2 times 4. So the top one would come to, what's that, 48? That would come to 144 over 8. And that would come down to a score of 18. So player A scored 18, player B scored 1. Therefore, the question is who won the game and by what margin? We can see that it's player A by 17, and that would be option D. Now the only other point here to make is that if you get to a situation in any part of UMAT where you've got this kind of equation here, which is quite complicated to multiply, just see if you can simplify. So you can simplify the bottom and the top, you can simplify individual numbers at a time. So you can cross out the 8 and the 4 there and just make it a 2 on top and a 1 on the bottom. Likewise, the 6 and the 2 maybe, you could turn it into a 3 and a 1. Don't be afraid to do it that way to make the numbers a bit simpler before you multiply them all together. But otherwise, I think it's a fairly straightforward question. The main issue is just reading it carefully and working out the order of the cards, which is a fairly common style of question. If we go to question 7, it's the final number-based question in this presentation. It's actually more similar to the 2 questions I did before, where we were working out the worst-case scenario. Again, I won't read all about that writing, but pause the video and take a minute to go through it yourself and have a go at it. In short, though, you can see that there's 11 pieces of chocolate. One's defective, which means that it will weigh differently on our balance scales here. And we're being asked, what is the maximum number of times you would need to weigh 2 pieces of chocolate, one on each of the 2 arms, in order to find this one defective piece out of the 11. So just imagine again the worst case scenario. The best case is that you find it immediately, that the first 2 you pick out, you put one on each of the 2 arms, and you get this imbalance as shown in the bottom. That's the best case scenario, that you immediately get that situation, and that means you only have to weigh one pair or one set of chocolates to find the defective one. The worst case is that you don't find that initially, and that defective piece is actually the 11th piece that you decide to put onto the scales. So in that case, imagine, again, I might just sketch it up quickly at the bottom. Imagine we've got 10 normal pieces. So I'll write 10 ends. And then just the 1D for defective. So this is the chocolates we have, and we're going to put 1 on each of the arms to see if we can find this imbalance where the scales don't equal each other, and in doing so we therefore find the defective one. So imagine the worst case scenario, which is that we just weigh all the normal ones to begin with. So we're weighing these 2 together, and there's no difference, so we still don't know which of the remaining ones is defective. We then weigh another pair, again, both normal, they're equal. We still don't know which of the remaining 7 are defective. So keep going, keep doing pairs like this. 3rd pair, still normal, 4th, and then 5th. At this point with the 5th, actually I'll go back a step. We'll just look at what happens after after we've done 4. So at this point we've done 4 different sets of measurements. They've all been normal. We've got 3 chocolates remaining, and we know that one of them is defective, but we still don't know which of those 3 are. So we do have to do that 5th measurement here. Now at this point, either that 5th measurement will be with a normal one and a defective one, so it could be like this, in which case there'll be an imbalance in the scales and we'll know that one of the pieces is defective. The other possibility is that we measure 2 normal ones again, in which case the scales would be normal, or equal rather. In that case though, you'd still know which one is defective because you would have just the 1 remaining piece of chocolate, and the 10 that you had measured before would have all been normal. So out of just a series of, or a process of deduction, you could know that that final piece would be the defective one. So either way, it's that 5th measurement where you would have to be certain one way or another that one is defective. You wouldn't need to go to a 6th measurement at all. So based on that, the answer here would be 5. I'm just going to finish off with a few questions that illustrate some principles of mental arithmetic. Obviously in UMAT you don't have a calculator, but occasionally you are asked to do some pretty tough calculations. So I'll go through a few little tips and tricks here to help make that a bit easier. So question 8, which of the following trials show the highest remission rate as a percentage? So you can see that we've got 4 trials here, A, B, C and D, and the first column shows the patients in remission, and the second one is showing the total amount of patients. So all we're really being asked is to work out the percentage, or rather we're working out this number here on the left as a percentage of the number shown on the right for each of the 4 trials. That's really all the question is asking. The difficulty is because we've got quite big numbers here. So how do we go about this? It's not really reasonable to expect you to have to work out an exact percentage down to a few decimal places. And you can see if we just go through, the best thing to do initially is just go through and get a rough approximation of what the percentages would be. And you can see for each of the 4 trials, I would say it's about 50%. The number on the left is roughly half of the number on the right. So the bad news is that means you can't make a rough approximation and get an answer just from that, because we can't tell just by looking at the numbers which is the answer, because they're all quite similar. But what it does mean is we can use the fact that they're all about 50% to our advantage. And the way I would do that is by working out what number of patients equates to a 50% remission rate, given the total number of patients here, and then seeing if the actual number of patients in remission is a bit above or a bit below that 50% mark. That might lead us to the answer. So to do that, all I'm going to do is divide the numbers on the right hand column by 2, so I'm just going to halve them. So 692, this is probably the trickiest part, is just dividing by 2, but it's still a fair bit easier than working out exact percentages. So 692, that would be 346. 332, that would be 166. 450, that would be 225. And 478, that would be 239. So the red numbers here show the numbers of patients in remission that would need to, the number of patients that would need to be in remission to achieve a 50% remission rate, given the total number of patients in each trial. So this is showing 50% remission rate. Now all we have to do is compare that number to the actual number here on the left and see whether the actual number is a bit above or a bit below that 50% mark. So you can see here, 343, that's a bit below 346. Just make that clear, that's a 4, not a 9. So the 343 here is a bit below 346. That means that the actual remission rate for trial A is a little bit below 50%. So it's a little bit below 50. In B, again, 165 is the actual number, and that's a little bit below the number that's required for a 50% remission rate. So it's a bit below 50. C, same story, fractionally below 50. But you can see in D, the actual number here is a bit above the number required for a 50% remission rate. And so for that reason, we can say that even though we don't know exactly what the percentage is, trial D had the best percentage in terms of remission rate out of all 4 trials, and therefore it's the answer. So this question is really just showing you how to approximate and then looking for kind of big, nice round numbers to help guide you. So in this case, it was 50%. If you're ever in a situation where you think the calculations required of you are just a bit too ridiculous to do, given the time pressure and given you have no calculator, always try and look for some shortcut. And one of them quite often is this one shown here. It is using that common nice round number as a kind of a start point and seeing how the other numbers compare to it. If we go to question 9, it's a similar story. So patients in remission, total patients in trial, trial A, trial B. So the table is the same. And the question is, which of the following is true about remission rates? So if we go through the answers here, you can see that basically on the left-hand side of each answer, we've got trial A. And we can see that the two answers are either just above 20% or just below 20%. Likewise for trial B, it's either just above or just below 40%. So it's similar to before where we use that 50% mark. In this case, we're going to use 20% for trial A and 40% for trial B. So to do that, what I'm going to do is say that with trial A to begin with, we're looking at 724 patients in total. So 724 is equal to 100% of the cohort. Now, I'm going to introduce you to another tip here. To find out what 10% or 1% of something is, just shift the decimal point. So if you want to work out what 10% is, we just have to shift down that decimal point and say that it's 72.4, and that is equal to 10%. Now that's 10%, and we're looking for the 20% mark. Just double it. So double the numbers here, 144.8, therefore equals 20%. That's a good, fast way of working out. If you're looking to find out what a percentage of a certain number, that's the approach I'd recommend. So if 20% is 144.8 patients, so I'll write that in here like we did before, but the actual number of patients who are in remission is 146, then our actual number is a little bit higher than our number which represents 20%, and therefore the number of patients in remission, or the percentage rather, is a bit above 20%. So we can assume that it's not option C or D because they're the ones which show a percentage a bit below 20. So it's not these two. It's either going to be A or B. It's the same process with option C. So again, it's 564 is 100%. Therefore, we can say that 56.4 is 10%. So I've just skipped that first step. If 56.4 is 10%, we want to work out what 40% is because that's the mark around which all these numbers are. So just quadruple 56.4 basically. So that would be 225.6, I think. Now, if that's our number for 40%, then have a look at our real number, which is 219. So that's a little bit below our 40% mark, which means that the remission rate will be a bit below 40%. So therefore, out of our remaining options, which are A or B, the answer is going to be this one here with the 38%. So that'll be A. And that's how you get to the answer here. So it's a similar process to before, just with the addition of this additional tip about breaking down numbers into 10% and or 1% if you require it, and using that as a building block to work out different percentages. So that's basically the approach for these types of questions. I think two more pretty simple ones, and this is just showing you how you can round and estimate quite often in UMAT. So in the previous two questions, all the answers have been very similar. The numbers have been, ballpark, in the same region as each other. So it's been very hard to round numbers without leading to inaccuracies. But in this particular question here, you can see that all the answers are very different from each other. There's big gaps between them. So if we're being asked, there are 411 patients in the hospital who each cost the hospital this amount of money, what's the total cost? Obviously, it's just a case of multiplying. So we're saying it's 411 times by 3691. I'm just going to illustrate how easy it is to come to answers when you round. So with this one, I'd be pretty comfortable saying, let's round down the 411 to 400. And to compensate, we'll round up the 3,700 to about 4,000. Then we just multiply the two 4s together to give 16. And we'll just add on the zeros. So we'll just do this like so. and given there are 5 zeros there, we'll put the 5 zeros on here. Just be careful with the number of zeros too, but you can see that the answer will come around to about 1.6 million, which is closest to option C. So all this is showing is just if you've got answers which are very different to each other, don't be afraid to round, and round quite heavily. In other words, make quite big jumps, as we did with the 3,700 to 4,000. That's fine. The other thing, I guess, is to compensate with rounding. If you round one up a little bit, maybe round the other one down by a similar amount, proportionally. But otherwise, you know, if you've got a nice big difference in the answers, then don't be afraid to do this. So the answer here would be C. Final question. Again, it's just showing you, same as before, if you've got answers which are very different to each other, which you can see here, you know, the percentages are very different. Don't worry about all the different zeros you might have. It's really just a case of working out, do worry about that, but it's more a case of working out not the specific number at the start, it's more a case of working out how many zeros or how many, or where the decimal point lies, more or less. So if we've got 120,000 people out of a total of 8 million, I would probably begin just by simplifying that. So yeah, again, make sure all the zeros are correct. I would simplify that by turning this 2 into just a 0, just to make it a bit easier. And then we'll just cancel out the zeros from here. So we can cancel out 1, 2, 3, 4, 5. And then again on the bottom, 1, 2, 3, 4, 5. And so you get down to basically 1 in every 80 people are smoking, just like that. At that point, you can work out, probably just intuitively, that if 1 in 80 smoke, and we're looking for a percentage, which is basically how many people out of 100 smoke, it's only going to be fractionally more than 1. So that percentage is going to be just over 1. So I would say pretty comfortably that I'd be happy with the answer of B, 1.5%. If you were tossing up between B and D, given they're both in the same ballpark, just look at the numbers we've got here at the start. So at this point, ignore the zeros and just look at the fact we've got 120,000 over 8 million. So it's kind of 12 over 8 effectively, and that will come to 1.5. So you know that the answer will have a 1 and a 5 at the start, whether it's 0.15% or 1.5% or 15%, it's going to be 1 and a 5. For that reason, and the reason before we simplified the zeros, the answer would definitely be B. So that's it for this video. A lot of the questions are a bit more, not simple, but they're a bit, I've cut away the narrative and the story behind the question and just focused on the maths and the probability and the arithmetic behind them. So in the real paper, you'll probably get more complex questions, but the maths that you have to do will be the same level as this. And so just remember those tips for mental arithmetic and probability, and you should be fine. So yeah, that's it for this video. Hope it helped.